Today we're going to talk about heavy oil crude blending. Um, that being said, a lot of what we're going to discuss today will actually be applicable to non-heavy oil blending. For example, you could have medium crude blending, and as we get into why do we blend, you'll see why we might want to do that. So, I'm just saying it's also applicable to non-heavy oil blending. So all the concepts are the same. Okay, so here's an outline of what we're going to be going through. You can see here all the topics we're going to try and cover in the next about 45 minutes or so. Why blend, blend stocks that are used, common specifications. We talk a little bit about vapor pressures, and then we talk about density, viscosity. Then we talk a little bit about as we calculate those things, there are manual methods that we can use. We can also use simulation software. So we talk a little bit about how that compares. We're going to do facility design basics right at the end. You see that these facilities are not very complex, but calculations are maybe a bit tricky. And then finally, we're going to talk about Asphaltene's precipitation, and then we'll wrap it up. Okay, so let's start with why would we want to blend heavy crude oil? And as I said, you might even blend non-heavy crude oil. So it's usually a combination of things. One of the main reasons why we might want to do this is because we have to. Somebody's given us specifications, they're buying our oil, and we may have to meet certain specs, which we're going to look at in a slide or two. So it might be meeting specifications. It might be for hydraulics reasons. So we're going down a pipeline and we need to reduce the viscosity. Or it might even be for treating. There are some companies out there, even in SAGD, that what they do is they'll actually blend upstream of an oil treater so that they don't have to be at a very high temperature. So if we wanted to upgrade crude oil, of course, we're going to talk about blending today. Are there other options? There are. And so you can see on this slide, we're actually talking about upgrading. So you could get the same effect from upgrading. You could either add hydrogen or remove carbon, and that would, both of those rather, would lighten up your crude oil. But those first choices that we just mentioned, they're pretty capital intensive and high operating cost as well. So blending is a very nice, inexpensive way of doing the same thing. And that is then you're able to reduce the density and viscosity of your crude oil. So, if I were to summarize it, it's pretty simple. It just involves the blending of a heavier crude oil with a lighter hydrocarbon liquid, which we're going to call a blend stock. So aside from, purely technical reason where we may want to change the properties or we might have to meet a specification, we can do this for pure economic benefit. So this is where we're taking a lower value blend stock, so something that maybe doesn't have as good a market, and it's a liquid, and we're going to actually blend it in with the crude oil. So what are we doing? We're obtaining a higher value for the blend stock fluid that we normally wouldn't get by blending it in the crude oil. So that extra volume of your blend, you're getting crude oil price for, which you normally would not have gotten. And, again, we said it before, but some of the other options are a little bit heavy on the capital cost, and this option happens to have a pretty low capital cost. So in the end, what we're looking for is increased revenue. And it's important to realize that is by blending a lower value blend stock into the higher value crude oil. And so what are some of the typical fluids we might use that are these lower value blend stocks that we could blend in? Butane's a good example, unstabilized condensate. Could also be NGLs or even a naphtha if we're near a refinery. So the key, though, is to find yourself a blend stock that has a lower value than the crude oil and be able to blend that in. For example, you could use other lighter hydrocarbons to blend in, but it might really not be as economic. A good example of that might be diesel. because it would fit the bill. I could really lighten up heavy crude oil by putting diesel in there, but it actually might cost or be worth more than the crude oil. So it doesn't really make any economic sense to do that. So what we're really looking for again, and the main idea then is to take a low value blend stock, low value compared to the crude oil that is, and blend it in. So let's talk about some of the specifications we might have to meet. The first one is density. It's not always specified, but quite often it is. And the value of density, if you were dealing with a heavy crude blend, is quite often specified as less than 940 kilograms per cubic meter. If you are blending for pure, like your own reasons, for example, I mentioned you might do that to make treating easier or for your own pipelining, then you might set your own density here based on, reducing density, reducing viscosity to make your pipeline transport easier. So depends again on the motivation, but specifications then might set this number. And typical specifications, that we have Plains Midstream for heavy crude oil, and it's one that specifies this less than 940. If we were looking at Pembina specifications, there are going to be different density specifications there, but that would be those wouldn't really be heavy oil. That's probably a more like a medium crude oil. So density typically for heavy oil is less than 940. If we use a lighter or a medium crude oil, it's going to be a different density specification. Or again, it might be just something that you specify if your blending is for your own processing. Another specification is viscosity, and it's often specified as kinematic rather than dynamic. And again, for heavy oil specifications, a typical number is less than or equal to 350 centistokes at something called ground reference temperature. Now, this ground reference temperature is a number that it's set by the sales, the company that you're selling to, and it's around 6 degrees C in the winter and moves up to about 18 degrees C in the summer. And in between, our in between numbers like spring and fall are quite often about 12 degrees C. So you would have to meet this 350 centistokes all year round. But as you can imagine, you're going to blend more in the winter because you're at 6 degrees C and your crude oil is going to obviously be at a higher viscosity, so you're going to have to blend more in. And sometimes you might end up at 18 degrees C where you have to blend very little or none at all. I should mention here that, if you are in that other case where you're looking at wanting to blend something into, let's say, a medium crude oil, it would not be 350 centistokes. So don't panic if you look at the Pembina specs and say, man, that's much different than what you said. Yes, it is. So in that case, you'd be blending for considerably different viscosity values. They're about 10 times lower, actually, something like that, 8 to 10 times lower. One of the issues that we can run into as we're trying to reduce the density and viscosity, or just plain economic benefit, is vapor pressure. So we're often given a vapor pressure about 70 to 103 kPa, and take note, these numbers are absolute. They are not gauge numbers. So yes, if you're thinking that, gee, 70 kPa is a vacuum, you're right, it is a vacuum. So as we go to blend, we cannot exceed the vapor pressure specifications for whoever we're selling the oil to, once again. So you would be blending to increase your revenue or change your properties, but you can't exceed this vapor pressure. There are two kinds of vapor pressure that we end up dealing with, where the specification is often in reed vapor pressure, or RVP, and occasionally in true vapor pressure. But the interesting thing is that from a calculation point of view, we're often dealing in true vapor pressure as opposed to reed vapor pressure. And we're going to talk a little bit more about that in the slide coming up. And then here we were just talking a little bit about specifications. So in Canada, Plains Midstream, as I mentioned earlier, or Pembina for lighter crude oils. So let's talk a little bit about these vapor pressures. True vapor pressure. So it is a thermodynamic property. It is the equilibrium vapor pressure. And it's the pressure below which vapor would actually liberate or evolve at a given temperature from your fluid. So in other words, if at a given temperature I'm below the vapor pressure, I get vapor. If I'm above it, I don't. So that is the pressure that we truly want to be above. TVP, unfortunately, though, is more difficult and expensive to measure in the field because getting to equilibrium takes time. And we see this actually quite often, even in other situations, like when we look at distillations. ASTM came up with a procedure for a different type of distillation. Why? Because the equilibrium true boiling point one takes too long and it costs too much. So it's a similar issue here, that TVP is really what we want, but it can be expensive and takes a long time to come to equilibrium, so time consuming and expensive. So a facsimile basically was developed many decades ago, something called Reid vapor pressure. And Reid vapor pressure is not a thermodynamic property per se. It's actually, there's a procedure, which you can see in the bullet here, that what we effectively do is we take our liquid, we put it in a sample container, and that sample container happens to have a 4-to-1 ratio of the fluid to air. So we have a valve open to the atmosphere. We have our fluid in the sample container. It's in a temperature bath, which is reduced to 0 degrees C or 32 F in this temperature bath. And once we reach that temperature, we actually close the valve. We increase the temperature of the system up to 37.8 degrees C or 100 degrees F. And then there's going to be a pressure that develops, and that measured pressure we read and record, and that is known as the Reid vapor pressure. So it's a facsimile to TVP. They're different, quite often not that different. But now we have two things. We have true vapor pressure, which is really what we're after, but it's something that's time consuming and expensive in the field. Reid vapor pressure, on the other hand, is less expensive and easier to do in the field. So, are there issues about TVP versus RVP? Yes, TVP can be calculated relatively easily by tools that we would use doing our engineering calculations. And RVP, on the other hand, is more difficult. So it is really the opposite of the measurement that I just mentioned, the field measurement. And simulators, for example, claim that they could all calculate RVPs very accurately. And you're going to see in a future slide, I kind of say that that's not entirely true, or at least not consistently anyway. So the design calculations and even operation of these facilities, because we're dealing with RVP and it's not that easy for us to get a consistently reliable calculation, can be tricky. So simple facility, maybe some tricky calculations. The implication of not being able to calculate RVP, very accurately, is that it might have to be measured in the lab to, during the design phase to verify our design. Or when you're doing field operation, you may want to be measuring RVP online. If you're going to do any lab measurements, what you want to do is measure the RVP of the crude oil itself prior to the blend, and then the blend stock itself and the blend. So you would want to get really 3 lab measurements of RVP. Minimum 2, which would be the crude oil and the blend itself, because the blend stock, you might actually be able to predict the RVP reasonably well, or just work backwards, actually. So again, saying the same thing, it's not that easy to calculate RVP accurately, or at least consistently accurately. The most reliable thing you can do is get it measured in the laboratory. Simulations can predict equilibrium properties, so really, if you think about it, a simulator would be better at predicting TVP. So, and I mentioned this earlier, simulators claim they can calculate RVP, which again, it's not an equilibrium property, it's an ASTM procedure, but they can't really do it reliably. And I'm not saying they're never good. What I'm saying is if you're going to use a simulator RVP value, be careful, and you probably should check it against a laboratory value and make sure that your particular simulation program is calculating RVP well. Again, most of the simulation companies will give you examples saying, yes, we can calculate D343 RVPs, and here's an example where we did it. The problem I ran into was that, yes, on the example problems, they work, and then when I tried to meet something else, it didn't really work, and that's really why I put the term consistently reliable in there, is that sometimes they're good, sometimes they're not. So you need to check. You should also know that if you happen to be able to calculate or get a TVP measurement or RVP measurement, and you want to move from one to the other, there are some pretty accurate correlations out there that allow you to do that. In other words, if you have a TVP and you said, well, I was able to get a TVP number from the lab, can I get a RVP from that? Absolutely. Let's move on to density. So calculating blend densities, we always probably would want to do the easiest thing possible, which would be just a volume fraction average density. And this kind of a density would be nothing more than saying, well, I'm going to take out of a blend, let's say I've got 80 volume percent crude oil and 20 volume percent blend stock. I want to take, okay, 0.8 times the density of the crude oil plus 0.2 times the density of the blend stock should give me the blend density. And it's actually pretty close, but there is something called shrinkage. There's an effect of shrinkage, and this has to do with just thermodynamic excess properties, which it's kind of like making a rum and Coke. If you put an ounce of rum in and 3 ounces of Coke, you'd say, I probably have 4 ounces, right? Maybe not. So that is the shrinkage effect. So how do we calculate shrinkage? Well, there are a couple of manual methods which are pretty good. And by the way, shrinkage is probably a number that's of the magnitude maybe around 0.2 to 0.5%, something like that. So it's not a huge number, but it's not definitely not negligible, especially, if you're blending in and you're dealing with several thousand cubic meters or barrels of fluid. So how do we calculate shrinkage? There are a few different methods, two of the really common ones that have been accepted by industry. The API 12.3 calculation you can see here in the middle of the slide. It actually calculates a percentage of shrinkage value, and it's based on having that volume percent of the blend stock put into this equation, as well as an API gravity difference. Now, that method has been used for decades. It's relatively accurate. In 1996, some people at NOVA said that, yeah, that's true, but they were finding some results above 30% blend that were starting to get less accurate with that particular method. So they came up with this polynomial you can see here, where you plug in the volume fraction of the blend stock. Up to about 30%, both methods will give you probably a very similar number. If you want to calculate density, then of your blend, first you calculate the blend volume, and we start with a unity number like 1 cubic meter or 1 barrel. It becomes 1 minus the shrinkage number, and then we can calculate the blend mass, which is going to be our volume percent or volume fraction of the blend stock times the specific gravity of the blend, plus 1 minus that number times the specific gravity of the oil. Once you have the mass, of course, density simple, it's mass per unit volume. So you could calculate your blend density that way. Blend viscosity. First of all, I want to say that simulations are really not great at calculating even crude oil viscosities unless you put some data in and ask your simulator to fit it for you. But if you were using a simulator, and I'm not picking on anyone in particular, any of them pretty much, and you ask them to predict crude oil density, they're not very good at it. So they're not good at that. They're definitely not good at blend viscosities either. So if you have actual viscosity data for your crude oil, sure, put it in and the simulator can probably fit it for you. But there's a difference between fitting and predicting. So I'm suggesting that you don't use simulators to predict crude oil viscosity. But if you have data, sure, put it in and they'll probably fit it well. Even if you do that and you argue that you've got a pretty good viscosity correlation because your simulator did fit the crude oil viscosity data, and you know that it actually works pretty well for the blend stock viscosity data, you still are probably not going to get the right blend viscosity. So there are some pretty good manual methods which have proven themselves over the years. They're kind of two distinct types. This first type is something that was developed by a gentleman named Shu in 1984. He was actually working with bitumen and condensate type blends. And he came up with this modified Lederer equation. It's called the Lederer equation. You can see here is basically a fraction times the log of viscosity of each of the components that I'm blending together. You'd then reverse that and get the viscosity of the blend. It's not uncommon, actually, if you look at how to calculate liquid viscosities. The trick is what is X? And it is a modified volume fraction here, and it's modified with something called alpha. And alpha was something that Shu came up with it totally empirically. There had been some speculation as to what it should be before. He basically reverse engineered everything and came up with what alpha should be. Delta rho there you can see is the difference in density between the two. So the alpha function then is based on the densities of the two fluids, the difference between the two, and then you can see there's a viscosity ratio there as well. So this is one method and one type of, or one way rather, to calculate blend viscosities. And you can see there that Shu's also using the dynamic viscosity. The second method that's quite common, and this comes out of the refining world, is you can't really blend viscosities linearly, but you could blend something called a viscosity blending index linearly, or a VBI. And both of these methods are common methods, and they are doing exactly that. They are actually linearly blending, and you're using the vapor the volume fraction rather, so that's XVI. So that's your volume fraction blended linearly with a viscosity blend index. So where the nonlinearity comes in is the VBI is not a linear function. So I've given you a couple of examples here of this type of technique. Here's a chevron index method at the top, and you can see their VBI is basically the log of kinematic viscosity divided by 3 plus the log of the kinematic viscosity. So there's the nonlinearity part. At the end, you simply reverse the procedure. So once you've got a VBI of the blend, which again is this linear combination of the VBIs, you just reverse it at the end to get the viscosity of the mixture or blend. There's also something called the Refutis method, and this method is just a slightly, well, I shouldn't say slightly different. It's a different nonlinear version of the VBI, and you can see there 10.975 plus 14.534. times the double log kind of function of the kinematic viscosity plus a constant. And again, you then calculate these individual VBIs, blend those linearly, and then reverse the procedure at the end. These types of methods have actually proven themselves to be relatively accurate. There are other methods. API came up with a method. It was originally a graphical method, so you had log paper, and effectively you plotted two viscosity points for your oil, as well as your blend stock on this log paper. The 2 points would be joined by a straight line. Then there was a methodology for basically coming up with what the blended version would be based on something called the lever rule, for those of you who might want to look that up in your thermodynamics textbook. But you'd use that lever rule to come up with the blended line on the log paper. Now, today, of course, it's not convenient. We like everything to be done in a computer. So there are numerical versions of this. And instead of using log paper, you can see there you can use something called the Walther equation, and that gets you your linearity by doing log of the viscosity. And of course, that doesn't look unlike what was happening in the Refutis method as well. ASTM also has an equivalent numerical method for doing this, very similar to the API method. So I would strongly recommend that you use these methods to actually calculate blend viscosity values rather than your simulator. So in addition to these properties, which in a way I've been picking on the simulators a little bit, but in addition to sort of having to check density and viscosity values of blend, and even dealing with vapor pressures, simulators also make some other assumptions that aren't exactly true in real life. For example, simulator will assume that your system comes to equilibrium, and that means you have an infinite time to come to equilibrium, which in real life, of course, we don't have infinite time. They also assume perfect mixing, and in real life, we don't get perfect mixing. So real life then is the opposite. It involves both a fixed time and there's a mixing efficiency. So those are things we have to consider. The other thing that's happened, and it actually happened to me on a project, was be careful when you're using a relatively light blend stock, because you may pull the lighter blend stock from a higher pressure down to a lower pressure that you're actually blending at. And if you do that, you might run into vaporization of the actual blend stock. And if you run into vaporization, again, what the simulator told me was no problem. Even though the blend stock partially vaporized, it didn't matter. The blend itself was all liquid all the way out to the tank, no problem. In real life, that didn't happen. We actually had vaporization coming off the tank and into a VRU. So what went wrong? Was the simulator so far wrong? No, it was just this equilibrium assumption. So if you end up at all with a vapor phase, you're going to need more time, and it's going to have to be a more efficient blend. So, really we try and avoid the blend stock itself being at all vapor. Facility design basics. Again, these facilities, they are not particularly complicated. So we'd have a tank of crude oil, we'd have a tank of blend stock. We're going to pump out of these tanks and we're going to blend together. But what we have to do, though, is blend to meet our specifications, but not exceed the vapor pressure, for example. So when we do this, we would want to have some instrumentation to measure those things. So typical facility, you definitely measure density, and it's preferable to measure viscosity. It would also be good to measure RVP. Unfortunately, measuring RVP is expensive. Okay, RVP analyzers are not cheap. So if there was another way you could do it without doing that, and I've run into several facilities like this where they don't really want to measure RVP, they just want to measure density and viscosity. then perhaps there's a way around it. And so if RVP is not going to be measured due to this cost, then you need some kind of indirect property. And one of the things I've done is you can start to do some blend calculations and figure out, okay, if I were blending and let's say I'm blending to less than that 940 kilograms per cubic meter we saw several slides ago, I might find that if I blend below, I don't know, I'm going to pick a number around 925, that particular density, if I go below that, I start to run into vapor pressure problems. How would I know that? Well, because I ran a bunch of calculations and I found out that, oops, if I go much below 925 kilograms per cubic meter, I'm going to be running up against the vapor pressure specification. So that's just an example of saying, using a surrogate property, if you will, or something indirect other than measuring the vapor pressure itself, and using that instead of the vapor pressure number that, of course, you're not measuring. So blend stock is added until the desired viscosity is achieved. That would be great. Or if the vapor pressure limit is reached. So what if you run into the vapor pressure limit and you haven't actually achieved your desired viscosity? Well, there's not a lot you can do about it other than go to a slightly heavier blend stock. So, and again, if you were using density, you might be finding, okay, well, I ran into this density limit, which I was using to represent vapor pressure, and I haven't quite reached my viscosity that I need to reach yet. So hopefully it doesn't happen, but it may happen to you on the lighter blend stocks. Things like condensate into crude oil, you can probably reach your viscosity before you reach the vapor pressure limit. So to maximize mixing efficiency, instead of just sort of routing some pipes together and hoping for the best, we'll actually use a static mixer. And just, I put this last bullet in there so that people realize static mixers require some turbulence, and you're going to require a reasonable pressure drop, probably 140 kPa or 20 psi for that to work well. And by the way, on this slide that I just went off, let me go back there for a minute. If you are, trying to use density indirectly, it's fine. It can work relatively well. But you may find, or you might have a situation that you'd say, well, I have like 12 different crude oils coming in and 2 different blend stocks that, are pretty common. So we have a range of crude oils and a range of blend stocks. Then if you don't want to measure RVP and you want to use a substitution property or surrogate type property like density, you have to do quite a number of calculations to figure out, with your range of crude oils and your range of blend stocks, that magic density number that I mentioned, you're going to have to run several calculations to figure that out. Okay, asphaltene precipitation. So one thing that can happen, particularly with asphaltic type crude oils and bitumens, is as we blend in the lighter liquids, we actually start to precipitate some asphaltenes out. And I've actually seen this happen accidentally at a blend facility. Ironically, not while they were blending, while they were down. Actually, some heavier crude oil backed up into the butane bullet, and it looked not unlike that picture that you're seeing there. So will we precipitate asphaltenes? There's a good chance we'll precipitate some. It's going to depend on the crude oil and the blend stock. So you should always check this and see if you're going to create some asphaltenes and how much. Unfortunately, it's not the easiest thing to do. We don't have any kind of fast equations like I showed you for some of the other properties that are the sort of 10-minute models. It's actually pretty complex phase behavior. And if you're going to check it, which I'm saying you should, you really should check it using a simulator. And so here the simulator comes in and becomes invaluable. or through lab tests. If you're going to use a simulator, you're going to need a SARA analysis, saturates, aromatics, resins, and asphaltene of your crude oil. And then that's going to have to get plugged into the asphaltene precipitation model. Will it be accurate? Maybe, maybe not. If you have any data, like even a single point that you measured in the lab, then probably becomes about an order of magnitude more accurate. That is the computer model. So without any data, it's better than nothing, and it'll probably at least get you a reasonable number. But if you have any data, and when I say data, I'm talking about a precipitation data point. If you plug that into the model and you can tune to it, it becomes much more accurate. If you don't have any of that available and you kind of say, well, I don't have a simulator and I can't do any lab work, are there any alternatives, or am I just sort of, I'm stuck? Well, there is an alternative. I'm not going to advocate it's a very accurate alternative, but there are several publications out in the open literature from various crude oils around the world with various different types of blend stocks, and many people have actually made these measurements to see if you're going to get asphaltene precipitation. And if you got lucky, maybe you'd find a similar crude oil, with a similar blend stock, and it might give you a very, very high level estimation of whether you're going to get asphaltene precipitation or not. Again, I'm not advocating that it's going to be the most accurate thing to do, but it may give you as I said, just a very high level estimation, and may indicate, when you have to do lab data. For example, if it looked like you were going to get a lot of asphaltene precipitation, you definitely want to do lab data. If it looked like you were only going to get a small amount, you might try and get away without lab data. I'm not advocating that, but you might. So what can we conclude from all of this? Relatively simple facilities. So heavy crude oil blending, it's an economic way of meeting specifications for either pipelining or your own treating, or just because you have to, or because it's a really economic thing to do. The facilities themselves, I didn't show you a picture, but I said it's really just some tanks and pumps, and then I put a static mixer in line. So the facilities themselves are not complicated, they're relatively simple. Your question around the facility design is really, what instrumentation am I going to use? Am I going to measure density, viscosity, and vapor pressure? Or we said vapor pressure is a little expensive, so we may not. Design operation calculations can be tricky, and it's really because of the blend versions of viscosity in particular, and the vapor pressures. So not only are calculations tricky, or can be tricky, actually operating the facility too, depending on what you're measuring. For example, I dealt with somebody recently that blew a tank roof off because they overblended, and then there ended up being a tremendous amount of vaporization, and they were not at all concerned about vapor pressure in this particular instance, and probably should have been. Talking to them later, they're also having problems with their pumps, so it's likely overblending. RVP should be determined in the lab if possible, as manual calculations and simulators are not consistently reliable. But as I said before, not to totally pick on simulation, if you found that simulation matched some lab data, sure, use it, because then it's probably going to be pretty good. Simulator blend density values need to be checked because they often overpredict shrinkage by about an order of magnitude. My experience has been they'll give me a few percent shrinkage when it should be, as I said, maybe like around 0.5%. Simulator blend viscosity values not recommended. Those blend calculations I showed you are much better. precipitation, we just talked about that, should be checked. And here's where a simulator will really come in handy, especially if you've got any data and or some lab work should be done. Okay, well, thanks everybody for listening to me drone on for about 45 minutes.